So tonight's presentation is a big one. It's called The Elusive Universe, Confronting Its Secrets. And before I begin, I want to inform everybody of how beneficial it was to work with Michael on the evolution of this presentation. Michael was very helpful in suggestions and edits, and most significantly, in advising me that this was really a two-part presentation because of the great amount of information that needs to be conveyed about the entire theme and subject. So tonight, part A, we're going to do the first half, and sometime in early 2026, we'll conclude. So that said, the elusive universe, confronting its secrets, for example, like this one. We'll be talking later on about the cosmic microwave background, which is the fingerprint of the Big Bang. Discovery of this in 1952 led to several important revelations about the beginning of our universe, but also posed many unanswered questions, which, as I mentioned, we will be seeing a little later, or confronting a little later. So the universe is arrogant. It dares us to understand it. So let's first reflect on this challenge and our place in the cosmos. According to Ray Bradbury, author and screenwriter, we are an impossibility in an impossible universe. Astrophysicist Neil deGrasse Tyson opines the universe is not obligated to make sense to you. And Alan Wilson Watts, a writer, speaker, and philosopher, says, through our eyes, the universe is actually now perceiving itself. And this concept is very popular among philosophers, by the way. Albert Einstein says two things are infinite, the universe and human stupidity. And I'm not sure about the universe. But the issue of stupidity aside, we contemplate the universe with a burning desire to reveal what it seems so determined to conceal from us. So this investigation poses four basic questions. And tonight we will devote ourselves to the first two. And the first one is, how long have we been trying to understand the universe? And number two, is the universe our friend or our enemy, and why? And I should point out that both questions have yielded some answers, and you'll see them. So the first question, how long have we been trying to understand the universe? And the answer is, since this man, Thales of Miletus, which was part of Greece at the time, but on the Turkish coast. And this was around the year 600 BCE. And Thales set aside mythology and religion and objectively asked, what is the common material that everything is made of? And his conclusion was water. But many people believe it really meant was a fluid, because he believed that the material had to flow easily to make it transform from one aspect of reality to another. But at least it was a start. We know about Thales because of Aristotle, who acclaimed him 200 years later, and his work has been preserved. So now we come to Democritus and the atom at about the same time as Aristotle. And Democritus and his teacher Leucippus theorized that the world was actually composed of tiny individual particles, which they named atoms, after atomos, the Greek word for indivisible. They believed that atoms were in constant motion and that different combinations made up everything. Now, that was really a remarkable deduction at a time that there was no scientific equipment to even test this theory. But a contemporary, Plato, took issue. He didn't like the atom theory because it could not be proved. Plato felt strongly that you must be able to see to believe. So science had from its beginning an attack from within, which is perhaps its greatest strength because nothing in science escapes attack until it's proven or disproven why it's so, and this is why it's so solid. So the concept of the atom remained a theory for 2,200 years until the 1800s and the early 1900s. And it took these seven scientists one by one to finally prove Democritus right and Plato wrong. Dalton proposed the theory of the atom, and the Curies found radioactive decay. Excuse me just for a second here. Well, I'm sorry, I didn't mean to do that. And Thomson, Rutherford, Einstein, and Chadwick all found different aspects of what constitutes atoms. But the atom is mainly empty space, and a popular dramatization pictures an atom the size of a baseball field. If in fact an atom was this big, the nucleus would be sitting on the pitcher's mound and about the same size, by the way, and the nearest electron would be at the center field wall. So therefore, the emptiness is really vast. Now let's look at a few significant cosmic accomplishments since the era of the Greeks. The first is Lemaitre and the primordial atom. The atom may be empty, mainly, but so is the universe, and its empty volume is actually increasing. And Georges Lemaitre deduced the expansion of the universe 2 years before Hubble proved it to be so. Now, Fred Hoyle was a very popular astronomer and scientist during my teen years. He was sort of regarded as the guru of astronomy, but he staunchly believed in a static universe, and he disparaged the idea of the primordial atom. And he, in his criticism, he coined the phrase Big Bang. To his shock, his term Big Bang became immortal. And Lemaitre was quite a guy. By the age of 9, he knew he wanted to be both a priest and a physicist, and so he was for the remainder of his life. By the way, he also studied at MIT and was associated with MIT. Gell-Mann and Zweig proved that atoms are not fundamental. In 1964, they independently discovered that tinier particles, which became known as quarks, built protons and neutrons. And the name quark comes from the James Joyce novel, Finnegan's Wake. And the line in the novel was 3 quarks for Mr. Mark. It seems actually, as you'll see, to be a very perfect name for these tiny particles. So although for the longest time the atom was thought to be composed of protons, neutrons, and electrons, in fact, protons and neutrons are not fundamental. Each one is composed of 3 far more tinier particles that we, as you know, are called quarks. The proton has what's known as 2 up and 1 down quark, while the neutron has 1 up and 2 down. And I'll explain this in a moment. Now, how do we know this? First of all, this seems amazing because you can't see quarks. They've never been detected outside of protons and neutrons, yet we know they exist and we know a great deal about their properties. It's because by bombarding protons with high energy beams of electronics, we found that they kept hitting 3 hard points inside. So quarks do not have whole number charges. They have fractional charges that sum up to +1 for a proton, each up being quark having a 2/3 charge and each down a -1/3 charge. and the neutron has a zero charge, it's neutral. And they are bound together by strong force particles named gluon. So that sounds pretty simple, right? You've got three quarks inside of a proton or a neutron, and they're held together by this force carrier that we nickname gluons. And however, unfortunately, it's not that simple. Inside every single proton and neutron in the universe, a wild party is going on. As noted physicist Sean Carroll explains, and here he is from Johns Hopkins, nucleons are actually complicated quantum configuration of quark and gluon fields. The adults, the valence quarks, have to contend with bizarre, unruly party crashers, other kinds of quarks, fields, and force particles. And let me give you an analogy. Let's say that you and two other very responsible adults rented an apartment, and you take very good care of it. You keep it clean, you pay the rent, you make sure the food is stocked, but the entire time that you're living in this apartment, there's a constant stream of other people who just wander in. They fill the entire confines of your apartment. They don't contribute anything really to the upkeep of it. They come and go at will, and you're stuck with them. Well, as it turns out, this is the case for protons and neutrons because their interiors are just filled with this collection, if you will, of quarks, fields, and force particles. But they are actually very important because they define the size of both the proton and the neutron and give them the correct mass. There you go. And there we go about it being vital. So how many of these wild parties are going on within, let's say, a single grain of salt? So here we have a grain of salt highly magnified. Well, a grain of salt contains 1 trillion molecules. And as we know, each molecule of salt is composed of atoms of sodium and chloride. So that's 2 trillion atoms. And because of the number of protons and neutrons that sodium and chloride possess, that comes up to 58 trillion quark parties in just a grain of salt. And just by comparison, your body contains 7 octillion molecules. So this is all we need to comprise the universe, meet the standard model. If we just had these 8 items on the left, we would have the entirety of our universe. The items being the up and the down quark, the electron, and the electron neutrino, or neutrino for short. We'll talk more about neutrinos in a little while. They're very ubiquitous. And then we need 4 force particles or force carriers. We need the photon, the gluon, and the 2 carriers of the weak nuclear force. So the photon, as we all know, is the carrier of the electromagnetic force. It spans the electromagnetic spectrum on the high end, high energy X-rays, and on the low end, low energy microwave and radio waves. And somewhere near the middle in a narrow band is visible light. So as you're looking at the screen right now, millions of photons are being emitted into your eye, and your eye's mechanism is registering those photons, sending the information to your brain, and your brain is constructing the image that you see. It's impossible to imagine a universe without photons. And as a matter of fact, photons came before anything else. The gluon, as we know from our short visit to the land of quarks, is extremely important. And the gluon, by the way, is an amazing force carrier because it's very much like a rubber band. It links together 2 quarks, and the closer together those quarks are, the weaker its power. The further apart the quarks become, the stronger it gets. So if you can imagine a rubber band that you put over 2 fingers, if your fingers are close together, the rubber band is quite loose. But as you expand your fingers, the rubber band becomes taut. And that's why quarks are never seen outside of protons and neutrons is because there's no escape from the gluons that are holding them together. And the Z and the W particles are responsible for radioactivity, generally among heavy elements that have a surplus of neutrons over protons. So you would think that if we have these, we have all we need, but no. As a matter of fact, we have to have these 17. There's 4 other types of quarks, and one of the things that I find to be most outstanding in the world of mathematics and science is that the other 4, the ones that are not constituting the important valence quarks in the electron, were all theorized and then proven through particle accelerators. Then we have 6 leptons. Now, leptons are tiny point-like particles that include the electron and the neutron. But lo and behold, we also have something related to an electron called a muon, which is a very heavy version of it, and one called the tau. And the neutrino, curiously, has a variation of each of these 3. And one of the things that it took some time to discover is that as neutrinos fly through space, and I'll just mention that they originate in fusion reactions inside stars in great abundance, but as they fly through space, they morph from one form to another. Then, of course, we have the 4 force particles we mentioned, in addition to the Higgs. Now, the Higgs particle, which made a lot of news about a dozen years ago, is responsible for the mass of all other particles that are related to mass. And that unto itself is an amazing thought, because it implies that throughout the entirety of the universe, there's a field that offers resistance to other particles, and that resistance translates into mass via the Higgs boson. And by the way, bosons is just simply the collective name for all force particles. But what's interesting here is that there is no graviton, which means that there's no particle yet known to convey the force of gravity, which is one of the 4, in fact, the first of the 4 fundamental forces. But that could be because of space-time, which Albert Einstein theorized through his theory of general relativity in 1915, and this could explain gravity without the graviton. And the idea of space-time is that it is stretched and, as you can see here, depressed by the presence of mass. That being the case, wherever there is mass, there's gravity. And John Wheeler, the noted physicist at Princeton, explained it pretty clearly. Space-time tells matter how to move. Matter tells space-time how to curve. Perhaps there's no need for a graviton. So the curvature of space-time could very well be the force, if you will, of gravity. And by the way, just for point of reference, Einstein's more famous theory of special relativity was conceived 10 years earlier. And now we come to Max Planck. Max discovered energy quanta in 1918, which changed everything. He later admitted his discovery was an act of desperation because it solved this problem of why electrons did not spin into an atom's nucleus. Never again would the universe work like Newton's clockwork. And just very briefly, the quantum world is what's happening inside of atoms. It is more based on probabilities, and the name quanta is significant because what Planck discovered is that everything that's measurable, be it temperature, be it time, be it length, is not continuous. It's actually increments in tiny quanta. As we know from studying, high school chemistry, electrons exist in orbits around the nucleus, and these are distinct levels. Electrons can only be in these levels, and that's what Planck discovered through quantum theory. Now, Vera Rubin produced the evidence for the existence of dark matter in 1980 after years of research. Rubin verified that the rotational rate at the perimeter of galaxies was much too fast. They should be flying apart, but they're not. Some unseen extra mass had to be responsible for countering the centrifugal force. And we finally detected this in studies of the Coma cluster. Fritz Zwicky actually theorized dark matter in 1933. Rubin was the one who actually verified it through her observations. Dark matter does not emit, reflect, or absorb light. It constitutes 35% of the stuff of the universe. It forms an invisible web. Visible matter, invisible web. Visible matter congregates at its nodes, which spawns galaxies, each held in place by a dark matter cocoon. But this is still very much observational without detection, because we know what effect dark matter has, but we have yet to detect any particles that could constitute this mass. Dark energy was discovered in 1998 by these three gentlemen. It is gravity repulsive and permeates all of space-time, much like the Higgs field. The expansion rate of the universe is increasing because more and more dark energy fills newly created space-time. At least that's what we theorized. Now, 5 billion years ago was a turning point in the life of the universe. Up till that point, gravity was more powerful than dark energy, and so the rate of expansion of the universe was slowing. But at the 5 billion year mark, the amount of dark energy in the universe with its repulsive quality was enough to offset the force of gravity. And ever since that time, we've been expanding faster and faster. We've also unlocked two more significant secrets in this century: gravitational wave and the Higgs field, which we talked a little bit about. The detection of gravitational waves is another proof of the general theory of relativity. And here's our friend Peter Higgs. And fortunately for Peter, he lived long enough for the Large Hadron Collider to discover his theoretical mass particle in 2012. So Homo sapiens have walked this planet for about 270,000 years. Our application of science spans just 1% of this period. So it's reasonable that we haven't had enough time to know all we seek to know. So keep this thought in mind as we turn our attention to what we know, and more importantly, what we don't know. So question number 2, is the universe our friend or is it our enemy, and why? Well, if we're limited to just these two choices, the answer, of course, is the universe is our friend. And if not, we wouldn't be here to contemplate the question. But in truth, the universe is a frenemy, not a friend or an enemy. Because without life support, it confines us to just portions of the Earth's surface and in the bottom 5 miles of our atmosphere. But I'd like to point out that if you were in the last mile or two, you would be in a lot of pain from lack of oxygen. So the question is, are we caged like pets? We are seemingly alone, restricted to operating equipment rooted to the surface or sent into nearby space, but to date, no more than a meager light year in distance. So how is it that the universe, though, did become a nursery for intelligent life, at least for us? Well, there's 3 possibilities. It's a happy accident. If not, humankind would not exist. 2, there are many universes, and we could only arise in one that was suited for life. Or 3, it is consciously designed to favor the emergence of life as we know it. So to better contemplate these alternatives, we first need to go back to just after the event that we call the Big Bang. So let's recreate the first post-Big Bang second of the universe. It is the most important single second of all time. And as a result, it is divided into 6 epochs. First, there is no flash of sound at the beginning. Photons are bound and will be for a very long time, and no medium yet exists to carry sound waves. So this is our initial universe after the Big Bang. It's silent and it's dark. However, lots is going on. A lot is going on. The Planck epoch is the very first tiny increment of time after the Big Bang. It's at the 10 to the minus 43 mark. And at that very early moment, the temperature is an amazing 1.4 times 10 to the 32 degrees Kelvin. And that's known as the Planck temperature, just as the Planck time is 10 to the minus 43 seconds. So Max Planck had many extremes named after him because of his fundamental role in quantum mechanics. And then here you can see here just how much, by comparison, cooler the sun's core is than is this first moment of time in the universe. At this point, all 4 fundamental forces are united, and the universe consists of pure energy. It's sometimes referred to as a quantum foam, and its size is the Planck length, which is 1.6 times minus 35 meters. It's an inconceivably small, size. At 10 to the minus 36 second, we come to the second epoch, which is the grand unified theory epoch. And the temperature falls to 10 to the 29th Kelvin. Gravity splits off from the other fundamental forces, and the universe still consists of pure energy. So the very first force, gravity, now makes its presence felt. And that very well could be because space-time is just starting to emerge. The third epoch at 10 to the minus 32 seconds is known as the inflation epoch. And at this point, the temperature continues to fall to 10 to the 26th. And in a split second, namely this amount of time, space-time expands from less than the size of an atom to that of perhaps a swimming pool. Now, that may not seem all that great, but proportionately, that's the same as a grape becoming bigger than the entire visible universe. And, a question that's often asked is, well, if the speed of light is the absolute speed limit in the universe, how is it that the universe could expand so rapidly and seemingly violate that speed limit? Well, the answer is it wasn't matter or energy within the universe that was expanding that fast. It was space-time, and there is no time limit on the expansion of space-time. And Alan Guth is the father of inflation. And it should be noted that just as quarks was whimsically named, Guth whimsically named this phenomena of inflation because at the time, inflation was all the news in the economy, and it seemed to be applicable. Now we come to the electroweak epoch at 10 to the minus 12th second. Temperature continues to fall to 10 to the 15th. And at this point, the strong force breaks off. So gluons are now free. Energy has converted into a Clark gluon plasma, and exotic particles emerge, including the Higgs boson, or Higgs, force particle. And at the end of this epoch, the electromagnetic and weak forces separate. So now we have 4 distinct forces. And as we know, mass equals energy over the speed of light squared, which means that a lot of energy converts into a little bit of mass. But as we know, there's a heck of a lot of mass in the universe. So you can imagine how much energy there must have been in order for it to have been uh, converted. Finally, or not finally, but now we get to 10 to the minus fifth seconds, which is the quark epoch. The temperature, sorry, I didn't mean for that to happen. The temperature falls further to 10 to the minus 12th. Quarks, leptons, and gluons flourish, but it's still far too hot for neutrons and protons to form. The hadron error, which are hadrons are basically any particle heavier than a proton, occurs at the 1 second mark. And this is very significant because the temperature now at 10 to the 11th Kelvin is cool enough for quarks and gluons to bind together and form protons and neutrons. Dark matter particles, whatever they may be, now exist. There is some scientific conjecture that perhaps dark matter particles came first, and from them came quarks and gluons. And then soon neutrinos will decouple and form the cosmic neutrino background. So finally, we get protons and neutrons. And here's a diagram that I think shows very well the three quarks inside of a proton and the elastic gluons that are binding them together. The temperature is now a balmy 10 to the 11th Kelvin. And by the way, point of reference, the diameter of a proton is 1.7 times 10 to the minus 17th meters. A quark is perhaps 10 to the minus 18th meter. This is the maximum it can possibly be. It may very well just be a point of no size. A long era now leads to the cosmic microwave background, the first stars, and the first galaxies. After 1 second, the universe continues to cool and expand, and over the next 380,000 years, hydrogen, helium, and some light elements form. And at 380,000 years, the universe has, because of the conversion into atoms, photons are finally set free, and the cosmic microwave background is now becomes visible. Stars and galaxies emerge. So I'll just take a moment here to say that during the era of inflation and the first 380,000 years, as atoms finally are able to form and stay together, that particular moment in time is for at least, as from our perspective, forever etched into this picture, if you will, of that moment, which we know is the cosmic microwave background, which surrounds the universe, the visible universe. Initially, these were high energy X-rays, but over the long distance that had to be traveled to reach Earth in the long period of time, the photons have slowed down into the microwave region, which is where the name comes from. And by the way, this particular boundary has been immaculately detailed and photographed through specific satellites, the Planck satellite in particular. At that moment, we now start to see the first stars. The first stars, thanks to dark matter, congregate and form galaxies. And now, after 13.8 trillion years, we are finally seeing the cosmic microwave background. And as you can see from the image on the left, some areas are hot, the orange areas, and some areas are different shades of blue. These cooler and hotter areas are actually, this, if you will, this irregularity is actually why we were able to, or why stars and galaxies were able to form in the first place, because of these temperature variations. But what needs to be mentioned is that these variations between the orange and the blue are in terms of millions of a degree. It's not as if they're red hot and ice cold. No, it's a very, very subtle difference. I also should point out that there is a mystery that the CMB has not yet been able to shed light on, although other experiments have. And that mystery is, why is there matter at all? Why in the world did there be a very slight abundance of matter over antimatter following the Big Bang? And let me just elaborate for a second. For every particle of matter, there is an equal particle of antimatter. And when they collide, they just turn into pure energy. Well, at the outset of the universe, there should have been as many particles of matter as particles of antimatter, which means, quite frankly, they should have annihilated each other, and then there would be nothing. And by the way, it didn't matter if antimatter or matter prevailed. We could have an antimatter universe with the same properties as the matter universe. What counts is that one or the other had a slight variation in magnitude. And we think that's because on the quantum level, there are quantum fluctuations, and that fluctuation during the first second of the universe was sufficient to make sure there was slightly more matter than antimatter. And then one final fact on the cosmic microwave background. There is one atom of matter that is imprinted on this background for every billion pairs of matter and antimatter particles that were annihilated. That just gives you an idea of how much matter and antimatter must have been created in the Big Bang. And now 13.8 billion later, 8 billion years later, this is what we see and know. But it's important to point out that what we're seeing 13.8 billion light years from Earth has now moved away to a distance of 46.5 billion light years due to continual expansion. So what we see on the edge of the universe is long gone from in terms of sight. It's just that we're seeing what was there 13.8 billion years ago. And eventually there will be no cosmic microwave background, which means a long way from now into the future, due to the continual expansion of the universe due to dark energy, scientists and astronomers on Earth won't have anything to see outside of the Milky Way galaxy. There will be no evidence for them of the cosmic microwave background. And some people have, in the scientific community, have contemplated, will this be considered just lore, much like we look back on our ancient ancestors who were so affected by the lore of deities and what we now consider to be humorous superstitions? Maybe. So how much stuff came out of the Big Bang? Well, the number of atoms net after matter-antimatter annihilation is 10 to the 80th power. The number of photons is 10 to the 89th power, and about 2/3 of those are in the cosmic microwave background. The number of neutrinos in the universe is 337 per cubic centimeter, which is about the same total as photons. Now, this mention, for the sake of mentioning it, that at every second, there are a million of these little particles that are penetrating your body, but neutrinos do not interact with particles that have mass. And so they generally pass right through. And it's been a devil for physicists to actually discover neutrinos. It wasn't until the 1980s, I think, that the first one was discovered in a vat of chlorine that was established. I can't remember if it was Japan, if it was elsewhere, but the notion was that a neutrino would eventually enter this tank filled with chlorine, hit the chlorine atom, and a krypton atom would emerge, and a detector would find it. Well, that was eventually proven successful, and many other similar experiments verified it. But the mystery was we were only detecting about 1/3 as many neutrinos as we should. But then when we learned that neutrinos change their color, change their stripes, if you will, and become muon or tau neutrinos, and we changed the experiment, then we found all the neutrinos that we thought we should. And then just a couple of other mentions. We have no idea of how many dark matter particles there are because we don't know how massive they are. There are some who believe that they are WIMPs, which stands for weakly interactive massive particles, which means that they are bigger than protons or neutrons, but we don't know. And we just don't know how many quanta of dark energy there may be. But we do know its effect, and we know that it's responsible for the expansion in of the universe. So the visible universe is what we're limited to seeing. I mean, what we're limited to seeing is how is any particular star or galaxy as far away as 27.6 billion light years, because that's how long it's taken the light from them to actually reach us. But we know that the universe is far more immense. As a matter of fact, it's at least 93 billion light years, and we have no idea what lies beyond the 93 billion light year mark. Some scientists believe it's infinite. Some believe it's at least double the 93 billion. So the other sad reality is we'll never know. By contrast, on the other extreme, it would take a line of at least 60,000 quarks to span the smallest atom. And if you go back to our example of the baseball field with the proton nuclei of, or proton nucleus of a hydrogen atom sitting on home plate, just imagine it would take 60,000 quarks to span that small space. So that's it for tonight. So stay tuned. Part 2 of this presentation is coming early next year. And then we're going to contemplate the 2 remaining questions. Question 3 is, what variables in the universe are fine-tuned in favor of life? And question number 4, how did the universe begin? So the elusive universe awaits you one more time. Thanks. Thanks, everyone.
Thank you.
Thank you, Phil.
Thanks, Phil.
Wonderful.
Thank you very much.
You have time for questions?
Gosh, I think so.
Um,
So what do you got,
Actually-
Arthur?
well, I'm just curious about a few things. I was watching a video, YouTube video on scale and sizes of things. And they made a comparison about our solar system and the galaxy. And they said, if you took the galaxy to the size of the United States, Atlantic to Pacific, Mexico to Canada, and that was our galaxy, the solar system would be the size of a red blood cell in
Yeah.
there somewhere.
Amazing.
And then the other thing was the size of the sun to the nearest star, which they said if you made the sun a millimeter in diameter, the nearest star is 30 kilometers away.
Yeah.
That's
Well-
why things don't run into each other when galaxies collide.
Yeah, so that what you have just helped everybody to grasp is that the universe is mainly empty space, and inside matter, inside atoms, it's mainly empty space, and inside protons and neutrons, it's mainly empty space, at least in terms of the permanency of the valence quarks. So perhaps that explains how everything could be compacted into a point at the origin of the universe.
It is truly an amazing story. And one last thing, when it comes to gravity, I'm kind of in the camp that it's not a fundamental force, but an emergent force, because considering the Big Bang was mostly energy and no mass,
Right.
it took 380,000 years before you got hydrogen, helium, and lithium to precipitate out, but there was still no mass, and mass is a distortion of the space it sits in, and
Right.
that is what we call gravity. And not, if you look for a graviton, that's like crazy, because you're looking at the distortion of space, not the mass in it. And they're looking for gravitons in the mass, and that's not where it's at.
Well, there's been I agree with you. I really do agree with you that it's the graviton is imaginary, because if you look at the history of discovery in science, there's always the popular theory that a large number of scientists just pursue doggedly, not realizing that there is a completely different way of looking at things that solves the problem. And somebody on the perimeter who's not affected by conventional thinking finds it.
Phil, can you hear us here?
Yeah, can you hear me?
Yeah, well, very well.
Okay, good.
We got a couple of questions in the room.
Let me just say one more thing before we move on. In part two, I'm just going to give you a little bit of a teaser. One of the absolutely most amazing things that I have to report is the triple alpha process, which is, again, one of these miracles of science that was never understood. But if we didn't have that, we wouldn't have life as we know it. And I'll explain all of this in the second part. Okay, I'm sorry. Go on with the next question, please.
Yes.
Go ahead.
Hi. Nothing goes faster than the speed of light.
Yes.
And the universe is supposed to be 13.8 billion years old.
Yes.
But how is it possible that the universe would be 93 billion years of diameter?
The answer is because it's space-time that's expanding more rapidly than the speed of light. Objects on the edge of the universe are already unto themselves expanding at the speed of light from our reference point, but objects that have already passed the visible limit of the universe have continued to accelerate, and the acceleration is many times that of the speed of light, because it's not matter itself that is flying that fast, it's space-time that's stretching that fast. It's amazing.
Thank you. Any other questions in the room?
Yeah,
Yeah.
you briefly touched on the asymmetry and the formation of hadrons. What was the time scale that evolved over?
That was all within the first second. And the other thing that's I don't want to get too much sidetracked, but because the universe was so tiny at that point, information was shared from one side of the universe to the other, which baffled scientists until they figured that out, because now, with the universe being as big as it is, the uniformity from one side to the other is so significantly the same that it seemed impossible for that. However, because the universe started off so small, whatever happened on the left side was known to the right side. And it was in that first second that this quantum fluctuation that led to a slight abundance of matter over antimatter to evolve.
Thank you.
Yeah.
Phil, Suraj has his hand up.
Yeah. Thank you, Phil, for amazing session.
Oh, thank you. Thank you.
I have a question about the cosmic microwave background radiation.
Yeah.
So first, how do we collected that data, and based on that data, do we pinpoint specially where the Big Bang happened?
Well, The answer that scientists give to the second question you ask is rather elusive, like in the name of my presentation. They'll tell you that the Big Bang occurred everywhere. And the reason for that is because everything in the universe is really a product of the Big Bang. But if we go back to Lemaitre for a moment, Lemaitre was the one who figured out that if the universe is expanding, it had to be going slower and it was smaller in earlier times. So theoretically, if you were to trace back all of the matter that was vectoring away from a common point, you could find that common point. At least that's what I think is true. And the first part of your question is that when the photons were set free at 380,000 years of age in the universe, they were all high energy X-rays. And there was an image, if you will, of high energy X-rays at the perimeter of the infant universe at that point, which continued to expand. And so now it's 13.8 billion light years away in all directions. And the photons, having taken that great amount of time to reach us, have slowed down to microwaves. So what we see as microwaves, which, by the way, if you ever had a raster television set, 10% of the static that you would get on your television set if you were at a channel that wasn't coming in was actually coming from the cosmic microwave background. So we have the image of it in microwave just because of the long period of time that it's taken for it to reach Earth.
I see. Okay. Thank you so much.
Yeah, you're welcome.
Thank you. Any other questions online?
Yeah.
What about in the room? All right, Phil, thanks a lot. That was really dandy.
Well,
Looking
thank
forward
you.
to the next one.
Presentation, Phil.
And thank you so much, Michael, for your guidance on this one. I couldn't have done it without you. Everybody should give a round of applause to Michael
Brilliant.
because, you
Sure.
know, we all present, or Michael finds these brilliant presenters to appear at GAAC, which is unto itself amazing. But Michael's contribution is, I kind of look at it as like Walt Disney. You know, Walt Disney used to say that he wasn't the one who went around and created the animation and the movies that were so popular, but he was the one who was like a little bee, spreading pollen around. And certainly with my presentation, Michael made a difference. So thank you, Michael.
Yeah, thanks,
Thank you,
Michael.
Michael.
Thank
That's
you,
a clap.
both of you. It was
You hear the
amazing.
clap?
I can clap.
Yeah.
Yay.
Testing with the new wireless rig. As everyone knows, end user testing is the first round of testing in any modern software project. Right.
Absolutely.
See you next month.
Get
Bye.
here. Bye, guys. Thank
Good
you.
night, everybody.
Thank you.
Looking
Bye,
forward to the
everyone.
next
Happy
one.
Bye,
Thanksgiving.
Chris.
Happy
Have a
Thanksgiving.
great week.
Happy Thanksgiving. We'll see you for the Christmas party.
Bye-bye.
Bye.
Bye-bye.
Wait.